let's see what buffer solutions are. So a buffer solution is one that will resist changes in pH when small amounts of strong base or strong acid is added. So it resists changes in pH when it's diluted as well. So when you keep adding water to it, the pH is not going to change by a lot. So this is a buffer. So a buffer may consist of a weak acid and its conjugate base, or a weak base and its conjugate acid. So there's two types of buffers. There's acidic buffers and then there is basic buffer. So let's see acidic buffer. So an acidic buffer will consist of a weak acid and its conjugate base. So for example, ethanoic acid is a weak acid and ethanoate is the conjugate base. So for weak acid, so ethanoic acid, because ethanoic acid is a weak acid would dissociate only slightly. And the conjugate base, the ethanoate ion here, so here you have the salt. So ethanoate, because it is a strong conjugate base, it's going to dissociate completely. So you have CH3COO minus. So there's going to be a lot of CH3COO minus in the solution. And also there's going to be a lot of the ethanoic acid into the solution because it is mostly undissociated. So the weak acid remains undissociated and the conjugate base is going to dissociate to give the ions of that weak acid. So which means that the solution has both of these ions. So you have a mixture of a weak base and a weak acid, and the conjugate base of this acid. So a mixture of a weak base, a weak acid and its salt. Now let's see what happens when we add a small amount of H plus to this. So we'll have an equilibrium position that is going to be disturbed when we add H plus or when we add OH minus. So we'll have to use Le Chatelier's principle to explain all this. So when you add H plus ions, the H plus is going to react with the ethanoate ions. And you'll have the weak acid which is going to be produced. So which means that any additional H plus that you add are absorbed by the CH3COO minus, by the by the conjugate base. So the H plus that are added are not going to change the pH, so the pH stays almost constant. Now when OH minus is added now, the OH minus from the alkali is going to react with the weak acid, and this is going to produce the conjugate base and water, which means that any OH minus that is added up to some extent, OH minus is going to be mopped out, maintaining the pH. So you can prepare an acidic buffer by dissolving the salt in a solution of the weak acid, or by reacting a solution of strong base with excess of weak acid. So remember, when you react a strong base with a weak acid, you get that buffer region in the pH curve. So that buffer region, this is where you have the weak acid in combination with the conjugate base of it. So weak acid and its salt. Now the other kind of buffer that we have is an alkali buffer. So now you'll have a weak base and the conjugate acid of that base. So let's say the weak base ammonia, which will dissociate partially, but the conjugate acid of ammonia, so NH4Cl, NH4 plus here is going to be the strong conjugate acid, and because it's a strong conjugate acid, this is going to dissociate completely. So the salt of the weak base is going to produce a lot of NH4 plus because it dissociates completely, and the weak base is going to dissociate partially, so which means that you're going to have a lot of NH3. So in the solution, you have a mixture of a base and its conjugate acid. Now, the conjugate acid and the base is going to maintain the equilibrium so that any H plus or OH minus is going to be balanced out. So when you add a small amount of H plus to it, the H plus is going to react with the NH3 so that it produces NH4 plus. So H plus is removed and the pH is maintained. But when you add a small amount of OH minus, the OH minus is going to react with the NH4 plus and it's going to give NH3 plus water. And so any excess OH minus that you're adding is going to be mopped up, so the pH is again maintained. So a basic buffer is prepared by dissolving a salt in a solution of weak base. So you have the weak base and its conjugate acid. So for this, you can use a titration of a strong acid and a weak base, and then at one point you're going to have the basic buffer. So here you get the buffer region where at half equivalence point pH is equal to pOH is equal to pKb. Now, a buffer has a certain capacity, which means that it's going to be effective at a certain point. So the more you have concentration of the components of the buffer, the more effective the buffer is going to be at maintaining pH changes. So a buffer has a capacity, and buffers are used to standardize pH meters. Those who have used a pH meter in their IAs know that you need to calibrate the pH meter. So this is done using a buffer. And you also have buffering in biological systems and maintaining pH of shampoos. Now, if you have a buffer, if you dilute the buffer, the pH will not change. So diluting a buffer has no effect on the pH, but it will change the buffer capacity, which means that if you take a buffer and add water to it, and then you add H plus or OH minus to that diluted buffer, the diluted buffer might not be able to maintain the pH. So it changes the buffer capacity, but it does not change the pH of the buffer. So dilution will change the buffer capacity. Temperature affects Ka and Kb values. Therefore, it's going to affect how the weak acid or the weak base is going to dissociate. So when you're working with buffers, the temperature is important. So you need to maintain a constant temperature when you are working with buffers. So when you're calibrating pH meters, you have to ensure that the temperature is the same. Temperature fluctuations should be minimized when you have blood transfusion due to the effect of buffers on the blood. So these are the factors that influence buffers.